So in class, we discussed this concentration profile where you have a liquid concentration X in the bulk and a vapor concentration Y in the bulk. These are the points that sit on the operating line. However, the points that are in equilibrium with one another are these points Yi and Xi, which sit on either side of the interface between the vapor and the liquid. So we need to develop a mass transport theory that explains this concentration gradient between the bulk vapor to the interfacial vapor and the bulk liquid to the interfacial liquid to relate these points on the operating line, Y and X, and the points in equilibrium at the interface, Yi and Xi. Let's set up two more points here. We're going to take this Y, this bulk vapor composition, and say that it would be in equilibrium with a liquid composition X star. Similarly, for the bulk liquid composition X, it would be in equilibrium with the composition Y star. So X and Y are points on the operating line. X star and Y star are points on the equilibrium curve, but X star is not in equilibrium with Y star. Rather, the equilibrium is occurring between X and Y. So the difference between the equilibrium in the bulk and the equilibrium occurring at the interface is going to allow us to determine the mass transport driving force that generates this concentration gradient, and it will allow us to get a relationship between equilibrium and mass transport for the system in this packed column. All right, in order to analyze that, let's take a look at what the operating line and equilibrium curve would look like. So we're going to draw on an XY axis, just like we always have, our equilibrium curve and our operating line. So we'll start with XY. And let's draw our equilibrium curve. And to make things simple, we're going to have an operating line straight in parallel with the equilibrium curve. All right, and let's think about a point A on this operating line. And this corresponds to our bulk, liquid, and vapor compositions X and Y. Now, if you think about this composition Y up here, this is the composition that is in equilibrium with our liquid composition X star. So if we draw a line over to the equilibrium curve, we get right here, and this point is going to be, it's the same Y, but now it's the equilibrium composition X star. So this becomes X star Y. Down here, if we draw a line at this point X to the equilibrium curve, this is the point at which X is in equilibrium with Y star. In order to figure out where our point at the interface, our Yi, Xi point sits, we're going to need to think about the mass transport equilibrium at the interface. And what we're going to say is that the rate of mass transport at the interface, call this R, is going to be equal to the rate of solute either entering or leaving the vapor phase. So this is going to be a precursor factor. We'll call this Kya, and I'll explain that in a second, times the driving force driving the solute to the interface. So this will be Y minus Yi. All right, so it's that concentration gradient provides the driving force pushing the solute to the interface. And whatever enters the interface needs to then enter the liquid phase in order to maintain mass balance. So the rate at which things enter the interface from the vapor phase needs to be equal to the rate at which they leave the interface into the liquid phase. So this is going to be Kxa times Xi minus X. The sign is opposite on these two because whatever is leaving the liquid phase at the interface enters the vapor phase at the interface, and vice versa. Now here, Kya and Kxa are lumped mass transport coefficients. So we're going to call KIA, where I is either X or Y, depending on whether you're talking about the liquid phase or the vapor phase, the mass transfer coefficient. It's expressed in these terms because Ki represents the mass transfer coefficient per unit area, and then A is the interfacial area. But in practice, we always lump these two together and treat it as a single coefficient. All right, if this is the case, we can rearrange these equations, and we get that y minus yi over x minus xi is equal to negative kxa over kya. In other words, we can locate the point at the interface. So this is going to be xi, yi, by drawing a line with slope negative kxa over negative kya from xy. All right, this is just an equation of a line going between xy and xiyi, and the slope of that line is going to be negative kxa over kya. All right, so we'll draw this. So we'll draw this line in as such, and we will indicate that this line has a slope of negative kxa over kya. Now, in order to relate the operating line to the equilibrium curve, we're going to define an overall mass transport rate. And this is going to be defined as R equals capital K sub ya. And again, the kya is a lumped parameter. We'll just treat these together. Times y minus y star. And this is going to be equal to kxa times x star minus x. Again, the signs are reversed because whatever leaves the liquid phase enters the vapor phase and vice versa. So you have to have the rate for the liquid phase is the opposite of the rate for the liquid phase. If one is negative, the other is positive. Okay, so this overall mass transport rate basically takes into account the driving force pushing the system towards equilibrium, whereas this mass transfer rate with the lowercase k's takes into account the driving force generated by the concentration gradient between bulk and interface. Now what we can do is we can solve this equation for y, and we can solve it for x, and we'll plug the y into this y and the x into this x. And if we rearrange the equations, we get the following. We get that 1 over capital Kya is equal to 1 over little kya plus 1 over little kxa times yi minus y star all over yi minus x. And similarly, we get 1 over kxa is equal to 1 over little kxa plus 1 over little kya times x star minus xi all over y minus yi. All right, so what we have here are two equations that take into account both the driving force pushing the system towards equilibrium and the mass transport driving force pushing the solute through the concentration gradient between bulk and interfacial concentration. To simplify these equations, we're going to go up to this diagram again, and we're going to start naming these points. All right, so let's call this point A. We'll call this point down here B. This point gets named C. This is D. And we're going to draw in 2 more points. Let's draw a straight line going out here and a straight line going up here. So this point gets called point E, and this point gets called point D. Okay, let's look now at these equations down here in terms of these points. Okay, so let's think first about this yi minus y star. Yi minus y star, yi here, y star here, sorry, yi here, y star here. So yi minus y star is simply going to become the length of the line segment ED. All right? So let's write it over here. Yi minus y star is equal to ED. Similarly, down here, xi minus x, xi minus x is going to be this line segment, BE. All right, so this ratio down here, yi minus y star over xi minus x, is simply this length, ED, over this length, EB. Notice that this is the same as the rise of this curve over the run of this curve, where this curve is the equilibrium curve, right? So what we're talking about down here, ED over BE, is equal to rise over run for the equilibrium curve, which is simply the slope of the equilibrium curve, which is the k value. All right, so this simplifies to the k value. Similarly, down here, we've got xi minus I star. All right, so, sorry, x star minus xi. So that's x star minus xi. That's this. And it's over y minus yi. Here's y minus yi. So this is run over rise for the equilibrium curve. It's 1 over the k value. So simplifying these equations, we have 1 over capital Kya is equal to 1 over little kya plus k over little kxa, and 1 over capital Kxa is equal to 1 over little kxa plus 1 over k times little kya. Right. In other words, the mass transfer coefficients describing transport through the interfaces are related to the mass transfer coefficients describing overall mass transport driven by equilibrium by the k values as follows. Now, in order to calculate the length of a packed column that's necessary to accomplish a given separation, what we're going to do is we're going to set up a material balance. And we're going to concentrate on the transport process from the gas phase into the liquid phase. So what we're going to do is we're going to say that the amount of solute removed from the gas phase is equal to the amount of solute absorbed into the liquid phase. A simple material balance. Anything that leaves the gas phase must enter the liquid phase. All right, and the solute removed from the gas phase is going to be the vapor flow rate times the change in concentration, negative sign because it's being removed from the gas phase. And then when it enters the liquid phase is going to be determined by mass transport. All right, so we'll say that this is just KYA, our overall mass transport coefficient. And remember, the driving force for here is the driving force to equilibrium. And in order to transform this from a linear value into a volumetric value, because this is in terms of volumetric, we need to multiply it by the cross-sectional area of the column and by the length of the column over which it occurs. All right, so this is the cross-sectional area of the column. And L refers to column length as it did in class. All right, we can write the same equation in differential terms. If we write it in differential terms, we get that negative V dy is equal to KYA times y minus y star SDL. And now to figure out how concentration changes over a given length of column, we simply integrate. All right, we're going to treat KYA, S, and V as constants. So we'll pull them all out, and we will get KYA times S over V times the integral between 0 and the total length of the column dl is equal to y out to y in dy over y minus y star. Okay, this integral is simple. It just goes to the total length of the column. So the total length of the column then is equal to V over KY A S times the integral between y out and y in dy over y minus y star. Now you might recall that we've already come up with a name for this integral. This integral is the number of gas phase mass transfer units, which we symbolize with n sub OG. It's possible to treat this, the right-hand side of this equation, as the product of two terms then, where this term, the integral term, is the number of gas phase mass transfer units, and the pre-term is referred to as the height of the gas phase mass transfer unit, HOG. All right, so this integral comes out to dimensionless. The value here is going to be a height. You multiply the number of units times the height of a unit. You get the total height of the column necessary to accomplish a given separation. So HOG is, in a way, analogous to the height equivalent to a theoretical plate. And NOG is kind of like the number of theoretical plates. It's only in special cases when NOG is equal to NT and HOG is equal to HOG. And that depends on basically how this integral gets integrated. It depends on the shape of the equilibrium curve, the shape of the operating line, and how the two are related to one another. Very briefly, and I'm not going to go through the actual math of the integration, but if we have parallel straight equilibrium curves and operating lines, all right, so something like, not like that, So if the equilibrium curve and the operating line are parallel and straight, close enough. Equilibrium curve, operating line, these are supposed to be parallel straight lines. If that's the case, then we have NOG is equal to NT, and of course, HOG then becomes equal to the height equivalent to a theoretical plate. In the case where the slope of the operating line is greater than the slope of the equilibrium curve, we have NOG greater than the number of theoretical plates. And in the case where the operating line has a lower slope than the equilibrium curve, we have NOG smaller than NT. If you have straight operating lines and straight equilibrium curves, so if both are straight, the following holds. The height equivalent to a theoretical plate is going to be HOG times ln of 1 over the absorption factor all over 1 minus the absorption factor over the absorption factor. And the number of gas phase mass transfer units is going to be the number of theoretical plates times the same ratio, ln of 1 over A all over 1 over A. Sorry, all over 1 minus A over A. Okay. It's also possible to come up with a general expression for the NOG, the number of gas phase mass transfer units, if you have a straight operating line and a straight equilibrium curve. Okay, so again, for a straight operating line and a straight equilibrium curve, you can integrate the integrand in the expression for NOG, right? So that integrand is simply 1 over y minus y star. All right, so the integral between y out and y in dy over y minus y star if the operating line and the equilibrium curve are straight, then you can plug known values in for the relationship between y and y star at every point, and you get this is equal to dy over 1 minus kv over L times y plus y out times kv over L minus k times xn. You can integrate this equation and you get that the number of gas phase mass transport units is equal to the log of absorption factor minus 1 over absorption factor times yn minus kxn parentheses here over y out minus kxn parentheses around here too close the square bracket, plus 1 over a, close the curly bracket, and this is all over a minus 1 over a. Right, this is simply taking the relationship between y and y star for a straight equilibrium curve, straight operating line, integrating it, and you get this value out here. And of course, a is the absorption factor. A is equal to L over kV. All right, so you can get the NOG, you can get the HOG. The HOG may be quoted for a given column, a given type of packing material, a given separation, and with those you can calculate the length of the column necessary to accomplish a given separation.